Alright, this video is going to be on the differentiability of piecewise functions. So whether or not you can say that the piecewise function is differentiable for its entire domain. So all of this that we're going to do in this video is based on knowing that if f of x and f prime of x are continuous, then the original function f of x is differentiable. So if you guys recall when we talked about differentiability, we said that in often cases, from what we've learned in calculus, piecewise functions are the interesting situation in a lot of these cases. So everything else might be kind of routine, but piecewise functions are the ones we have to pay more attention to. So in the first example, we're going to say that our original function is x squared plus 1 if x is less than or equal to 1. And 2x if x is greater than 1. So the first thing we want to do to check to see if f of x is continuous is we want to see basically if there's a hole there at 1 or a jump, So we know that x squared plus 1 is a polynomial function, so those are always continuous. So for this part where x is less than or equal to 1, it's definitely going to be continuous. 2x also, well, that's a straight line, but that's also continuous. So the only thing we're really concerned about is what happens at 1. So I'm going to go ahead and check. I'm going to say 1 squared plus 1. I need these two things to equal for them to be continuous. If I have those y coordinates, because that's what I'm finding, I'm plugging in x to find a y coordinate. If those y coordinates are the same, that means that those two pieces of the graph come together at the same point. If those y coordinates are different, it means that I have a jump happening. So this would give me 1 plus 1 is 2, 2 times 1 is 2. So we're going to say that this piecewise function is continuous on negative infinity to infinity. So I wasn't really concerned about most of it, I was only concerned about 1. So now I need to check the derivative to see if the derivative is continuous. So I'm just going to take the derivative of each piece. So the derivative of the first one is 2x if x is less than or equal to 1. Derivative of the second piece is 2 if x is greater than 1. I'm going to check this also to make sure that those y values match up as they should. And if these two are both continuous, then I can say overall it's differentiable. So I'm going to go ahead and plug in 1. I got 2 times 1. For this side is just 2, and that checks out. So we're going to say that the derivative is also continuous. And so because of that, we can make the conclusion that f of x is differentiable on negative infinity, infinity. All right, we're going to try another problem doing the same thing. So this time we're going to say we have x squared plus 2 and x plus 2 as our piecewise function. And it's x squared plus 2 if x is less than or equal to 1. And it's x plus 2 if x is greater than 1. So again, we want to check to see that the y values match up. So I'm going to say 1 squared plus 2 needs to equal 1 plus 2. And that's 3 equals 3, that's true. So we're going to say that the original function is continuous. And then I'm going to go ahead and check the derivative. I don't even have to write the plus 0 there. That was me kind of getting ahead of myself. The derivative of x is just 1. So this is if x is less than or equal to 1, if x is greater than 1. And then I'll go ahead and plug 1 in. So 2 times 1 needs to be the same as just 1. Those two things do not equal each other. So we are going to say discontinuous. At x equals 1, that means there's a jump discontinuity there. And so we're going to say f of x is not differentiable at x equals 1. It's going to be differentiable everywhere else, just not at that one point. Okay, we're going to do, I've got 2 more examples here. We just need to do one. I think that these are going to get pretty boring because they're all kind of the same. So we're going to say f of x is 3x plus 2 if x is less than or equal to 1, and x to the third plus 4 if x is greater than 1. And 1 is not the magic number, it just happens to be what we're using in all of these. So you could do the same thing at 5 or 6 or whatever. Both of these pieces are polynomial functions, so that means that I'm not worried about the continuity of this straight line when x is less than 1. I'm not worried about the continuity of this cubic graph when x is greater than 1. The only thing that I'm worried about is what's happening at 1 exactly, because it could be a jump there. So I'm going to check and make sure my y values are the same by plugging 1 in for x. So we've got 3 plus 2 is 5, and 1 plus 4 is 5. So the original function is continuous on all real numbers. And then I'm going to go ahead and find the derivative. So the derivative of 3x plus 2 is just 3. The derivative of x to the third plus 4 would be 3x squared. And then again, 1 is where we're interested in the problem. So I'm going to say, if I plug in 1 here, I just still have 3. If I plug in 1 here, and you can see that those two things are equal each other. 3 really does equal 3, so this is continuous. And since both of the graphs are completely continuous, then we're going to say that if f of x is differentiable, on negative infinity, infinity.